Today we're going to finish off our last topic that's required for our unit test on Monday. It's called the law of conservation of mechanical energy. We've talked over the last number of days now about energy, the two types of energy, kinetic energy of motion, potential stored energy. We've learned that we can convert one to the other. When a car goes down a hill, we convert gravitational potential energy to kinetic energy as the car speeds up. As it goes up the hill, we convert kinetic energy that we had at the bottom of the hill to potential as it gains a higher height. We've learned about work as well. Work is the change in energy. An object can experience a change in energy or a change in a certain type of energy by applying a force on it over a certain displacement, force and movement, right? Today we're going to talk about the energy essentially of a system if we have a nice closed system or isolated system where we don't have any external forces or external factors coming into play. Okay, the law of conservation of energy says that the energy in that system will always remain constant. In other words, it's not going to change. It's not going to increase or decrease. We're not going to create energy, and we're not going to destroy energy. If we account for everything, if we account for all the little factors that change energy from one form to another, then the total energy will always remain constant. This is the first conservation law that you're going to learn. Next year in Physics 30, you'll learn a couple more conservation laws. They all start off the same way. Blank cannot be created or destroyed. Energy cannot be created or destroyed. Momentum cannot be created or destroyed. Electric charge cannot be created or destroyed. Conservation means stays the same. So if we're talking about conservation of energy, then energy stays the same. It can't be created and it can't be destroyed. But it can be transformed from one type to another. So you can have lots of potential energy that 5 seconds later you don't have anymore. But it has to have been transformed or converted into something else. Like kinetic energy or whatever. Now sometimes there is energy added to the system from wind or from an applied force, or in 2.5 weeks when you do your physics of amusement park field trip, you go up that roller coaster, that 50-meter high hill on the Mindbender roller coaster. Sometimes we have a situation like that where a motor and a chain is adding energy to the system. But in the end, we still haven't created it. It's coming from somewhere. If we account for everything, including the energy, the electrical energy that's going into the motor, then we would find the total energy would still remain the same because it can't be created. And sometimes it looks like energy is lost, destroyed. It's not. Sometimes it's taken away from a system. Maybe we've got friction or air resistance, and maybe when slam on the brakes of your car, you come to a stop, you've lost energy, you've destroyed energy, right? Well, you haven't destroyed energy, not at all. You've converted kinetic energy into thermal energy or heat energy. You notice when you slam on the brakes of your car, you get these black skid marks on the pavement, right? You ever notice that, black skid marks on the pavement? Okay? You don't notice that on concrete nearly as much. Do you know why? Do you know why? Like concrete is white. You think you'd notice the black skid marks more on concrete than you would on pavement, right? But you don't. There's two reasons why you notice it more on pavement than you do on concrete. One is because pavement and tires have a higher coefficient of friction, which means a higher force of friction, which means more energy is taken away from the system. But the other thing is, when you slam on your brakes and you skid on the pavement, or on the cement for that matter, you're actually generating enough heat to melt tar in the pavement. So your skid mark is partially rubber from your tire, but it's also partially tar from the pavement kind of coming up to the top. And you don't see that in the cement, right? So when you slam on the brakes of your car, is energy destroyed? No. Kinetic energy is taken away, but it's just converted to thermal energy and some sound energy as well, right? When you hear that car skidding. If we account for everything, though, we would find that the total energy, right, the total energy that we had, which was kinetic, and the total energy that we have afterwards, which is thermal energy, sound energy, whatever, stays the same. We don't create or destroy energy. Now, if we solve problems where we're basically saying this and this are small enough values that they're insignificant or negligible. In other words, we have so little energy added to the system, or zero energy added to the system or taken away from the system because of wind or air resistance or the motor in the chain or whatever. If all the types of energy that we have in the system are just the kinetics and the potentials, the obvious ones, then we can solve a problem by saying EI equals EF. If the total energy remains the same, if energy isn't created or destroyed, then the initial energy will be equal to the final energy. The energy that we start with is going to be equal to the energy that we end with. Let's draw a picture of a hill. This is maybe the first hill on the Mindbender. You know what, it's not actually, because the first hill on the Mindbender is 50 meters high and way steeper. It's pretty much straight down, 50 meters free fall straight down. How many people have ever ridden that? Well, 2.5 weeks from now, hopefully all of you will have ridden it. Once you get past that first 50-meter straight down drop, though, it's like easy after that, right? Let's say we've got a height of 50 meters here. Let's say we've got a roller coaster cart at the top of the hill moving at 5.0 meters per second. And let's say we want to find out how fast that roller coaster cart is moving at the bottom of the hill right here. We say EI equals EF. I'm not going to actually solve this problem, guys. I just want to set it up here to explain to you what types of energy we have. And then we'll do an actual example problem where we'll actually crunch some numbers and solve it. EI equals EF. We've got to ask ourselves a couple of questions. The first question is, do I have a height? At the beginning of this problem, do I have a height? Do I? Yes, I do. It's 50 meters. If I have a height, then I have what? Potential energy. Now, that is if we're defining the potential energy relative to the bottom, right? Then I would have potential energy. If I'm defining it relative to the top, then I wouldn't have potential energy. But it wouldn't make much sense in this case to define it relative to the top. So, relative to the bottom, yes, I do. I have potential energy. Now, the second question that you have to ask yourself is, at the top of this hill, is it moving? Is it moving? Yes. If it's moving, then I have kinetic energy, right? So be careful here. You're going to add, not multiply, but you're going to add kinetic energy. We're going to say the total mechanical energy, by the way, is kinetic plus potential. So the total mechanical energy here is mgh plus 1/2 mv squared. Now, at the end of this problem, which is in this case at the bottom of the hill, what kind of energy do I have? Well, do I have a height? No. So there is no potential. Is it moving? Yes. So I do have kinetic energy. So this is what the equation would become. mgh initial plus 1/2 mv initial squared equals 1/2 mv final squared. All right, let's change this around a little bit. Let's say now I want to find the speed halfway down. Not when it reaches the bottom, but halfway down. Does that change my initial energy? At the top of the hill, like I still have potential because I've got a height, and I've still got kinetic because it's moving. But at the end of the problem, which is halfway down the hill now, is it moving? Yes. Does it have a height? Yes. So now it's got kinetic and potential energy at the end of the problem. Does that make sense? You're going to have potentially kinetic and potential at the beginning and kinetic and potential at the end. You just got to ask yourself, do I have, which ones of these do I have at the beginning and the end? And the way that you identify that is with two questions. Do I have a height? And is it moving? If I have a height, I've got potential energy. If I've got movement, then I've got kinetic energy. Does that make sense? What if we were going the other way? What if we had this car that was moving at 10 meters per second down here, and let's say when it gets to the top, it's moving at 4 meters per second. How would we deal with that? Well, we'd still say that the initial energy would be equal to the final energy. What kind of energy do we have at the beginning here? Well, it could be kinetic and it could be potential. What kind is it? It's kinetic because it's moving. Do I have a height at the beginning? No, I don't. So there is no potential at the beginning, right? At the end of this problem, do I have a height? Yes. So I've got potential. Is it moving? Yes. So I've got kinetic. So what's happening in the first case? In this first problem, we've got, well, we start off with lots of potential and a little kinetic. Potential gets converted to kinetic as it goes down the hill. We lose potential, we gain kinetic. What's happening in the second problem? Well, we start off with lots of kinetic, but as we go up the hill, that kinetic gets converted to potential. We lose kinetic and we gain potential. All right? This question may look different than the questions, than the setup that we just did with the roller coaster, right? But it's really the same thing. This time we're throwing a ball downward. So we're throwing it straight downward versus a roller coaster cart going down on a hill. It doesn't make any difference. At the top of this, right before the ball was thrown, or as the ball was thrown, it has a certain amount of energy. When it reaches the ground, it has the same amount of energy. The initial energy is equal to the final energy. At the top of this, or as the ball is being thrown, we would say it has kinetic energy because you can see that it's being thrown at a speed of 5 meters per second. But you can also see that it's being thrown from a certain height. So it's got initial energy, mgh. Now, when it hits the ground, does it have a height? No. Does it have movement? Yes. As it hits the ground, it's got kinetic energy. So we'd say 1/2 mvf squared. We would sub in our numbers here. Oh, you know what I just noticed? There's a shortcut here. Has anybody spot it? Yeah? Good. We got an m in every term, so we can cancel that out. Can't cancel it out if it's only in true terms, but if it's in all the terms, we can get rid of it. We don't have to. We can leave it as 0.5 kilograms. That would be fine. Give us the same answer, but it saves us a little bit of work this way. We're going to say 1/2 of vi squared, which is 5.0 plus 9.81 times the initial height, which is 335, equals 1/2 of vf squared. Notice I'm actually subbing my numbers in before I rearrange this one. Doesn't really matter. 0.5 times 5 squared is 12.5. 9.81 times 35 is 343.35. Now let's add those two numbers together. And then let's multiply it by 2 or divide by half. And then let's square root it. And we end up getting 26.7. So how fast is this ball moving when it reaches the bottom? 26.7 meters per second. Right? Yeah?
I tried doing it where, like, I took, like, half the mass, like, from that side.
Half the mass from
From the final.
I'm not sure what you mean there. All right, just as a hopefully quick little aside here, some of you, when you saw this question, may have thought, I can already do this question. I don't need conservation of energy to do this question. I might say VF squared is equal to VI squared plus 2AD. Right? How many people were kind of thinking that in the back of their minds, like, why don't I just do that? That works, right? That works if it's a nice vertical problem like that. That works. We just got another tool in the toolbox now. But what I want to show you guys is something here real quickly. If we take this equation right here, 1/2 mv squared plus mgh equals 1/2 mv squared, and then we cancel out the m's, we're left with this, right? 1/2 of vi squared plus gh initial equals 1/2 vf squared. Let's solve for vf here. Okay, let's solve for vf. Let's take the half over to the other side. We're going to do that by multiplying by 2. That's the way we take a half over, is either divide by half or multiply by 2. If we multiply this by 2, we get vi squared. If we multiply this by 2, we get 2gh. If we multiply this by 2, we get vf squared. So if we just change the order of it, take this to the left side, take the other to the right side, we end up with, using conservation of energy, vf squared is equal to vi squared plus 2gh. Or vf squared plus vi, or is equal to vi squared plus 2, what's g? A, right? Same as A, 9.81. What's H? Same as the displacement. So using conservation of energy, we end up really doing the same thing. Does that make sense? That's where that equation comes from. All through kinematics, we use that, and you just trusted me that it's a valid equation. This is where it comes from, is the law of conservation of energy. All right? What I'd like you to do right now is work on a couple questions from a worksheet that I'm about to hand out to you. All right, having a look at question number 1, just before the bell goes, it says, a student on the roof of the school throws a 500-gram ball off the edge of the school at a speed of 15 meters per second. The ball is moving at a speed of 24.5 when it hits the ground. How high is the school? And describe the energy transformations that are taking place here. We're going to say EI equals EF because we know that the total amount of energy remains constant. We don't create or destroy energy. What kind of energy do I have on the top of the school? Do I have a height? Yes, Ben, so that means I have potential energy. So we're going to say MGH, initial, on the top of the school. Do I have movement? Is the ball moving on the top of the school, Erica? When it's being thrown off the top of the school, is it moving? Yes. So I've got kinetic energy. We're going to say that's 1/2 mv squared. Do I have a height when it reaches the ground? No, Megan, I don't. So I don't have potential. Is it moving when it reaches the ground? Yes, so I have kinetic energy when it reaches the ground. All right, so it's going to look like this. Once again, m appears in every term, so I can make that disappear. I can cancel it out. Left with g times h initial. We're going to say 9.81 times the initial height, which is, that's what I'm looking for, I guess, isn't it? How high is the school? Plus 1/2 of the initial speed squared. It's 15 meters per second. Now, we don't know which direction that is, but it doesn't matter because kinetic energy and speed are scalars, so it doesn't matter whether it's thrown straight out or straight down or straight up. It doesn't make any difference. Equal to 1/2 mvf squared, 24.5 meters per second. So which way is that moving? Once again, it doesn't matter whether it's straight down or whatever. Okay, in the end, it's moving at 24 meters per second. That's the speed. Okay, so we're going to say here 9.81 times hi plus 1/2 of 15 squared. Gives me 112.5 equals 1/2 of 24.5 squared. Gives me 300.125. Let's take the 112 over by subtracting. So we're going to say 300.125 minus 112.5 gives me 187.625, and then we're going to divide that by 9.81, and we get a height here of 19.1 meters. So the height of the building is 19.1 meters. Now, what are the energy transformations that are taking place? It's actually pretty straightforward. There's one transformation that's taking place. What is it? Like what's decreasing here? What kind of energy are we losing? What kind of energy are we gaining here? Megan? Right, we're losing potential, we're gaining kinetic. So the energy conversion that takes place is gravitational potential energy to kinetic energy. Does that make sense? Okay, if you're not finished question number 2, finish that up for homework tonight. And then we'll take a look at your unit assignment tomorrow and then question number 2 if we need to tomorrow as well.